Scientists at CERN are at the edge of their seats, eagerly anticipating breakthroughs from the world's largest and most powerful particle accelerator. The Large Hadron Collider, a marvel of modern science crafted by the European Organization for Nuclear Research, has shed light on numerous scientific puzzles. Just now, Brian Cox has announced that something terrible has happened at CERN that no one can explain. During a test with unprecedented energy levels, CERN scientists encountered something unexpected and potentially unsettling. Could this discovery provide more insight into the universe's secrets, like miniature black holes? And how is this discovery related to the Mandela effect? Let's find out why this mystery has left even the most seasoned researchers scratching their heads.
So what does CERN do? Well, it's a machine. It's the most complicated machine ever built by many measures. And its job is to explore the universe because we're interested in how the universe works. This machine accelerates protons, so the nuclei of hydrogen, to 99.999999% the speed of light. It accelerates them around. When they're going at full speed, they travel around that ring 11,000 times a second. There are two beams of them, one going one way, one going the other way. They're compressed into something which is the diameter of a human hair. They're crossed. And in those collisions, in every proton-proton collision that's generated there, up to 600 million every second, by the way, we recreate the conditions that were present less than a billionth of a second after the universe began. Why do we do that? Purely because we want to know how the universe works. So a tremendous engineering achievement. I could say, actually, this whole thing runs at a temperature less than minus 271 degrees Celsius, which is 1.9 degrees above absolute zero, which is colder than the universe. So a lot of people say that if it wasn't for a technological civilization like ours, there would be nowhere as cold as that in the universe. And as I said, its job is to create the conditions that were present a billionth of a second after the universe began.
CERN, known as the European Organization for Nuclear Research, is a real powerhouse in the world of science, on a mission to uncover the deepest secrets of the universe. Tucked away near Geneva, straddling the border between Switzerland and France, CERN has become legendary for its groundbreaking work in particle physics. Ever since it kicked off in 1954, CERN has been at the forefront of delving into the tiniest building blocks of matter and the forces that hold them together. But lately, there's been some buzz, and maybe a little bit of concern, about what's been going down at CERN. Thanks to some recent experiments, including ones that made headlines on the Joe Rogan Show, there's been a mix of awe and puzzlement in the air. One of CERN's biggest claims to fame is its discovery of the Higgs boson, famously dubbed the God particle. This elusive little guy, first theorized by physicist Peter Higgs and his pals back in 1964, had been giving scientists the slip for decades until CERN finally caught it in action. So why all the fuss about the Higgs boson? Well, it's a big deal because it's a key player in something called the Standard Model of Particle Physics. This model basically lays out the rules for how particles interact with each other, and the Higgs boson is like the linchpin holding it all together. It's linked to this thing called the Higgs field, which is like this invisible energy field that supposedly fills up the entire universe. And get this, the Higgs field is thought to be responsible for giving particles their mass, which is pretty crucial for, stuff like forming atoms and, well, life as we know it. And then there's the Large Hadron Collider, or LHC, which is basically like the crown jewel of CERN. Picture a big old ring of super powerful magnets and high-tech gizmos, all designed to boost particles to crazy high energies. Inside the LHC, these particles zoom around at almost the speed of light before smashing into each other head-on. It's like controlled chaos, all guided by these super fancy magnets cooled down to temperatures colder than outer space, to make sure everything stays on track. Now let's dive into what makes the collider at CERN so mind-blowing. This bad boy can whip up proton collisions with an energy level of a whopping 13 tera-electron volts, making it the big kahuna of particle accelerators. When these protons smash into each other, it's like a cosmic fireworks show, unleashing a whole slew of new particles for scientists to geek out over. It's like taking a peek back in time in the moments just after the Big Bang, giving us a glimpse into the very fabric of the universe. But none of this would be possible without the super sleek detectors strategically placed around the collision points. These babies are like the eyes and ears of the operation, meticulously tracking and recording every little particle that pops out of the collisions. They're like high-tech Swiss Army knives, with layers upon layers of technology, all designed to catch, track, and measure the energy of different types of particles. Once all of that data is gathered, it's time for the real fun to begin. Physicists from all over the globe roll up their sleeves and dive headfirst into analyzing the data, hoping to uncover some juicy insights into everything from the elusive Higgs boson to the mysteries of the universe itself. But here's the kicker. It's not just a one-person show. It takes a small army of physicists, engineers, and tech wizards from all corners of the planet to keep the Large Hadron Collider running smoothly and making sense of all that data. And speaking of data, we're talking serious numbers here. The CERN data center churns through a mind-boggling 1 petabyte of data every single day, equivalent to a cool million gigabytes. And just like any high-performance machine, the LHC needs a little TLC every now and then. So it operates in cycles, alternating between periods of intense action and downtime for maintenance, upgrades, and all that jazz. Let's shine a spotlight on what happens during these shutdowns. It's all about making upgrades to boost the collider's luminosity, which basically means cranking up the collision rates and churning out even more juicy experimental data. Now let's talk about the big kahuna, the discovery of the Higgs boson. This little guy confirmed the existence of something called the Higgs field, this invisible stuff that fills up all of space and gives particles their mass. It was like plugging a big hole in the standard model puzzle, giving us a clearer picture of how the universe ticks. But the fun doesn't stop there. Thanks to this discovery, we've opened up a whole new can of worms in particle physics. We're talking deep dives into the very fabric of the universe, trying to unravel the mysteries of what went down right after the Big Bang. And as if discovering the Higgs boson wasn't cool enough, CERN's impact goes way beyond just particle physics. Ever heard of the World Wide Web? Yep, you can thank CERN for that. Sir Tim Berners-Lee cooked up this game-changer back in 1989 as a way for physicists around the globe to swap info. Little did he know, it would revolutionize the way we share and access information, totally transforming the world of communication and technology as we know it. But wait, there's more. CERN's fingerprints are all over the place, even in the field of medicine. They've helped develop all sorts of fancy tech that's making waves in the medical world. Advancements in particle tech are changing the game for medical diagnostics, starting with positron emission tomography, or PET scans. These rely on detecting particles emitted by a radio tracer, giving us detailed images of the human body that are a game changer for diagnosing and treating diseases like cancer. And guess what? CERN's not just shaking things up in the world of particle physics. They're making waves in computing and data analysis too. All those fancy techniques they've cooked up to handle insane amounts of data pouring out into the LHC? Well, turns out they're super handy in other fields too, like aerospace and finance, where crunching big data is the name of the game. But wait, there's more. CERN's also paving the way for some serious upgrades in medical imaging, thanks to their work in superconducting technology. See, those super fancy magnets they use to steer particle beams in the LHC? They're also the secret sauce behind the next-gen magnetic resonance imaging, or MRI machines, giving us even sharper images for diagnosing all sorts of ailments without exposing people to radiation. CERN's groundbreaking experiments are shedding light on the mysteries of antimatter and pushing the boundaries of science to new heights. By diving deep into the world of antimatter, CERN's research isn't just expanding our understanding of the universe. It's opening doors to potential breakthroughs in energy and material science. One of their star players in this game is the antiproton decelerator, a cutting-edge machine that lets scientists study antimatter particles with unprecedented precision. This kind of research is like peering into the very fabric of reality, giving us a better grasp of the fundamental differences between matter and antimatter in the grand scheme of things. But with great power comes great responsibility, right? There's been some chatter, especially on a recent podcast episode with Joe Rogan, about the potential risks lurking within CERN's experiments. Folks are raising questions about whether tinkering with particles in the Large Hadron Collider could inadvertently kickstart some seriously spooky stuff, like creating black holes or setting off other catastrophic events. Now, let's pause for a second. While these concerns might sound like something out of a sci-fi movie, they're rooted in a real fear of the unknown. It's like stepping into uncharted territory and wondering what kind of wild stuff we might stumble upon. But here's the thing. There's no solid evidence to back up these worries. At its core, CERN's research is all about delving into the weird and wonderful world of quantum mechanics. Quantum mechanics constitutes a foundational theory in physics, elucidating the physical properties of nature at the scale of atoms and subatomic particles. It forms the basis for CERN's experiments, including those conducted within the Large Hadron Collider, diverging from classical physics by introducing concepts such as superposition and entanglement. These concepts propose that particles can simultaneously exist in multiple states and be interconnected despite distance. One of the most intriguing and debated interpretations of quantum mechanics is the many worlds theory, which suggests the existence of potentially infinite parallel universes alongside our own. Each universe represents a distinct outcome of every action, decision, and event. Within the framework of CERN's experiments, where particles collide at high energies, the many worlds theory theorizes that the results of these collisions could diverge into separate, coexistent realities. In these parallel universes, every conceivable possibility comes to fruition. For example, in one scenario, a specific experiment at CERN could yield one outcome, while in another scenario, it could result in a completely different outcome. This notion corresponds with the quantum mechanical principle suggesting that particles exist in a superposition state, embodying multiple potential states simultaneously until observed or measured. The implications of the many worlds theory for CERN's experiments are extensive and primarily theoretical. If accurate, the high-energy particle collisions within the Large Hadron Collider unveil fundamental aspects of our universe and potentially interact with these parallel universes. This interaction might offer insights into the nature of these alternate realities, although it remains purely theoretical. Furthermore, the many worlds interpretation provides a distinctive perspective on causality and decision-making. In a vast universe where every conceivable outcome materializes in parallel worlds, the concept of choice and consequence assumes a novel significance. Another enigma central to quantum mechanics, and consequently to experiments conducted at CERN, is the measurement problem.
There's something called the quantum measurement problem, which has been with us since the early days of quantum mechanics. How do you go from the fuzzy, hazy reality of quantum probabilities, where things can be in many locations with different likelihoods, to the single definite reality we observe when we do a measurement? We don't know how we go from one to the other. Even so, we can still test quantum mechanics. We do the observations and simply determine how often we see a particle at one location or another, and we hope that those frequencies match the probabilities that come from the mathematics. But we've not been able to fill in the details of how to go from the fuzzy probabilities to the definite reality we all observe.
This quandary stems from the principle that the attributes of particles remain indeterminate until measured. Prior to measurement, particles such as electrons exist in a superposition state, capable of occupying multiple states simultaneously. However, upon observation or measurement, they seemingly select a specific state. This peculiar aspect of quantum mechanics poses a challenge in comprehending the true essence of phenomena observed in experiments like those conducted in the Large Hadron Collider. When particles collide at high speeds, the observed outcomes may represent just one of numerous possibilities, prompting inquiries into the nature of reality and our capacity for full comprehension. In comprehending the recent discourse led by Joe Rogan regarding CERN's recent experiments, both quantum mechanics and the many worlds theory play pivotal roles. Given this comprehension of parallel universes, Rogan posits whether it's plausible that the scientists at CERN inadvertently opened a pathway to a parallel universe. Another key figure advancing this discourse is Max Laughlin, renowned in theoretical physics for his unconventional insights into CERN's experiments. Acknowledged as a prodigy within the scientific community, Laughlin garners attention for his exceptional intellect and adeptness in grasping intricate scientific theories from a young age. Driven by his passion for physics and an innate ability to grasp intricate theories, he emerged as a figure of interest with intriguing, albeit contentious insights into particle physics. Laughlin's propositions regarding CERN, particularly concerning experiments at the Large Hadron Collider, have sparked concern. He proposes that the high-energy collisions within the Large Hadron Collider might create gateways to alternate dimensions. Laughlin suggests that these experiments could unintentionally initiate encounters with realms of reality yet to be discovered or explored. Despite Laughlin's assertions, the scientific community, renowned for its stringent standards of evidence and peer review, remains skeptical of his theories. Most physicists and researchers consider his ideas speculative, lacking the empirical evidence necessary for scientific validation. Despite the groundbreaking nature of CERN's experiments, the mainstream scientific community asserts that they adhere to established physical laws. Concerns regarding the creation of portals to other dimensions, as suggested by Laughlin, are generally disregarded as beyond the current scope of scientific comprehension. Figures like Rogan and Laughlin have raised concerns about the potential for these experiments to manipulate reality or shift dimensions, a topic widely discussed. These apprehensions arise from the immense energies involved in particle collisions and the exploration of uncharted territories within quantum mechanics. Speculations surrounding CERN's experiments encompass concerns about the potential creation of black holes, disturbances to the space-time continuum, or inadvertent access to alternate dimensions. The notion that CERN's experiments might generate black holes stems from theories suggesting that high-energy particle collisions could result in the formation of minuscule black holes. These hypothetical black holes would be microscopic and short-lived, evaporating almost instantaneously through a process called Hawking radiation, named after the renowned physicist Stephen Hawking. However, CERN scientists and the broader physics community have largely dismissed these apprehensions. They argue that if such black holes could indeed be generated by the energy levels achieved in the Large Hadron Collider, they would also be produced by high-energy cosmic rays naturally striking Earth's atmosphere, yet no harmful effects have been observed. Disrupting the space-time continuum represents another speculative risk associated with CERN's experiments. This concept is a common theme in science fiction, often depicted as causing significant disruptions in the fabric of reality. Scientifically, this would entail alterations in the fundamental forces or constants of nature that uphold the universe. While intriguing as a theoretical concept, there's no empirical evidence or theoretical framework within current physics to support the possibility of such disruptions resulting from human-made experiments, such as those conducted at CERN. Speculation about inadvertently accessing alternate dimensions stems from theories in physics proposing the existence of additional dimensions beyond the familiar three-dimensional space and one-dimensional time. Some theories, like string theory, suggest that these extra dimensions could be compactified or concealed at scales currently beyond our experimental reach. The hypothesis suggests that high-energy collisions, such as those occurring in the LHC, could momentarily unveil these higher dimensions. Nevertheless, this concept remains purely theoretical without any empirical evidence to support it. As scientists venture into uncharted territories of knowledge, they grapple with the ethical responsibilities accompanying such advancements. Ethical deliberations encompass concerns regarding potential environmental ramifications, experiment safety, and the broader societal implications of these scientific breakthroughs. A continuous dialogue ensues regarding the equilibrium between scientific exploration and the prudence required when dealing with phenomena and particles whose properties are not entirely comprehended. While the pursuit of knowledge is imperative, it must be balanced with an understanding of the potential far-reaching effects of groundbreaking research. Joe Rogan has delved into these moral and philosophical quandaries during his discussions, particularly reflecting on the ethical dilemmas posed by CERN's endeavors. He contemplates the ethical obligations of scientists when conducting experiments that could hypothetically yield hazardous and unforeseeable outcomes. Rogan also adopts a critical stance, questioning the moral dimensions of such pursuits and the associated risks inherent in pushing the boundaries of human understanding. One of his significant concerns, shared with Laughlin, revolves around the Mandela effect. The Mandela effect describes a phenomenon in which a significant number of individuals recall an event or detail differently from its recorded history or reality. Coined by Fiona Broome in 2009, the term originated from a widespread false collective memory of Nelson Mandela's death in prison during the 1980s, despite his actual passing in 2013. This phenomenon underscores the fallibility of human memory, susceptible to influence from various factors, resulting in the shared misrecollection of specific events or details among large groups. The Mandela effect encompasses numerous instances where public recognition diverges notably from documented history, such as the collective memory surrounding the Berenstain Bears children's book series. Many individuals remember the name spelled as Berenstain Bears, despite the correct spelling being Berenstain Bears. Similarly, a widely known example involves the misremembered line from the film Star Wars: The Empire Strikes Back, where the iconic phrase is actually, "No, I am your father," rather than "Luke, I am your father."
I am your father.
These instances of the Mandela effect extend beyond pop culture and into historical events. For instance, some people vividly recall watching the live television broadcast of the Challenger space shuttle explosion in 1986, although it was not aired live on national television. The Mandela effect is also evident in the misquotation of famous lines. A prominent case is the widespread belief that Mahatma Gandhi once said, "Be the change that you wish to see in the world," a quote that cannot be found in his documented speeches or writings. The prevalence of these false memories prompts intriguing inquiries into the intricacies of human memory and perception. Psychologists attribute this phenomenon to a myriad of cognitive biases, memory distortions, and social influences. The human brain exhibits a remarkable ability to fill in memory gaps with false, yet seemingly plausible information that aligns with existing beliefs or prevalent narratives. Within the realm of CERN and its experiments, particularly those conducted with the Large Hadron Collider, speculation has arisen regarding a potential link between the Mandela effect and alterations in quantum states. The hypothesis proposes that high-energy particle collisions might impact the fabric of reality, potentially causing minor yet significant alterations in our timeline or collective memory. According to this notion, alterations at a quantum level, possibly occurring during experiments at CERN, could propagate to the macroscopic level, resulting in widespread collective false memories among the populace, reminiscent of the Mandela effect. This association between the Mandela effect and CERN's Large Hadron Collider experiments is grounded in the intricate and often enigmatic realm of quantum mechanics. The Large Hadron Collider's capacity to collide particles at extraordinarily high energies and observe the ensuing phenomena offers fertile ground for theories suggesting that these experiments could exert far-reaching, albeit subtle effects on the very fabric of reality. The concept revolves around the notion that quantum events occurring at CERN may extend beyond the microscopic level to have more widespread and perceptible effects. One theory suggests that during particle collisions within the Large Hadron Collider, there could be brief disruptions to the stability of the space-time continuum. While these disruptions are incredibly small and transitory, they could theoretically result in slight changes to humanity's collective perception of reality, potentially contributing to the Mandela effect. Furthermore, the theory speculates that these disruptions at the quantum level could explain minor yet observable inconsistencies in mass memory, such as shared misrecollections of historical events or cultural references. Another facet of this theory revolves around the concept of quantum entanglement, wherein particles become linked and influence each other's states instantaneously, irrespective of distance. Some theorists propose that the high-energy collisions within the Large Hadron Collider could generate entanglement ripples that extend beyond their immediate surroundings, potentially impacting the broader fabric of reality in unpredictable manners. Additionally, it's hypothesized that if parallel universes or alternate dimensions exist, as certain interpretations of quantum mechanics suggest, then the experiments conducted at the Large Hadron Collider might briefly intersect with these alternate realities. Although highly speculative, this interaction could result in subtle overlaps or exchanges between parallel timelines, giving rise to collective false memories. Critics of this theory contend that there is no empirical evidence to validate such a connection and argue that the Mandela effect can be more plausibly attributed to psychological factors influencing human memory. Experts highlight that the current understanding of quantum mechanics does not support the notion that particle collisions could significantly influence human history or memory on a large scale. Several alarming incidents at CERN have heightened public concerns regarding the activities within the facility. Although the Large Hadron Collider has greatly advanced our knowledge of particle physics, its operation raises apprehensions about potential unintended consequences, particularly at maximum energy levels. A primary worry revolves around the potential impact of these high-energy experiments on the Earth's magnetic field, which serves as a crucial shield against solar winds and cosmic radiation. There is apprehension that the intense energy and magnetic fields generated by the Large Hadron Collider may somehow disrupt or alter this natural protective barrier. Another area of concern pertains to the potential influence of the Large Hadron Collider on solar storms, which can disrupt various Earth systems, including satellite communications, navigation, and power grids. There is a fear that any disruptions caused by the Large Hadron Collider to the Earth's magnetic field could render the planet more susceptible to these solar disturbances. There's apprehension that such vulnerability could lead to more frequent and significant technological disruptions, potentially impacting millions of people. The possibility of a global blackout, leaving the world devoid of technology and electricity, looms as a crisis of apocalyptic proportions. It's crucial to acknowledge that these concerns are predominantly theoretical. The Large Hadron Collider operates within established safety parameters, with no concrete evidence suggesting that its experiments have adverse effects on Earth's magnetic field or increase the risk of solar storms. Decades of scientific research and technological advancement have contributed to the design and operation of the LHC, under the supervision of prominent physicists worldwide. CERN has conducted comprehensive safety assessments and external reviews, affirming the safety of the Large Hadron Collider experiments. Studies have indicated that any potential black holes or strangelets produced by the Large Hadron Collider would pose no threat. The cosmic rays naturally impacting Earth with higher energy levels than those generated by the Large Hadron Collider have proven harmless, providing additional reassurance regarding the collider's safety. Although scientific agreement on this matter remains elusive, influential figures such as Joe Rogan and Max Laughlin have sparked widespread discussion, heightening awareness about these experiments. While the outcomes of the peculiar experiments at CERN remain uncertain, global attention towards CERN and the Large Hadron Collider has significantly intensified. The interest in CERN and the Large Hadron Collider extends beyond scientific circles, captivating the public imagination and fueling a plethora of discussions, debates, and even conspiracy theories. While the scientific community strives to understand the fundamental building blocks of the universe and unravel the mysteries of quantum mechanics, the broader society grapples with the implications of such endeavors. At the heart of these discussions lies a tension between scientific progress and ethical considerations. On one hand, there is a desire to push the boundaries of human knowledge and unlock the secrets of the universe. On the other hand, there is a need to proceed with caution and ensure that the pursuit of knowledge does not inadvertently lead to harm. The concerns surrounding CERN and the Large Hadron Collider are not limited to potential disruptions of Earth's magnetic field or the occurrence of solar storms. There are also fears about the creation of microscopic black holes or strangelets, hypothetical particles that could potentially pose a threat to the stability of the universe. Thank you for joining us. Please be sure to give this video a thumbs up if you enjoyed watching it.